I did not. Mm, so noise floor. Ha. Forget about the slides. Let's talk about noise floor. Something that we can easily understand. When you go to the market, Taki or Lagos, like Oshodi or whatever, the way you talk, you have to increase the way you talk. You have to not really shout, but then you speak a little bit louder than when you are in. You guys have MQ theater. We used to have that. That was the largest. Or then in school, just have MQ. Ah, yeah, okay. So the way you're talking to each other in MKO, when the class is so full, is you have to speak a little bit louder than when you're in your bedroom and you have a visitor. You're in your room and you have a visitor visiting you. You can even whisper. Sometimes we call it bedroom voice, right? You can just hey, what's up? How you doing? Whatever. Oh, this stuff. Oh, okay. You can even whisper, and you will hear yourself clearly, loud and clear. But if you try to whisper, what do you say to the other guy in the local theater? You say, "Can you speak louder a little bit?" I can't hear you. I can't hear you. Speak louder. Okay. Even though the other person talking is talking in the same um, way as a, in the as it was talking, it was in the bedroom or the living room, same way in the markets or MQ or whatever. The difference in the different scenarios is because of the noise floor. The way our hair is a receiver, our mouth is a transmitter. The way our hair is the same way radio frequency is generally on antennas. Unlike us that we have a transmitter and receiver separate, just like you have in sound in audio, in acoustics, you have a mic and a speaker. In the radio frequency, most times you have a single antenna that we call them transceivers. So it's the transceiver, the transmitter, and the receiver. So the transceiver. So the receiver sensitivity is what I've just explained to you. For the receiver sensitivity, for you to be able to identify, to distinguish between the actual signal and the noise floor, you need enough of delta. You need enough of separation, yeah, between the actual signal, the amplitude of the actual signal, and the amplitude of the noise floor. So if it is not so clear, distinct enough, then you find it difficult to understand. That is when we say, can you repeat yourself? But you hardly say that when you're in your living room watching, talking to each other. But you can change the scenario in the living room. Let's say you're in the living room talking, and all of a sudden you increase the volume of your TV or your radio or the sound system, and it becomes very loud. You've increased the noise floor. At that time, you have to tell the other person to speak louder, and that's the concept of noise floor. Let me show you something. Back to my the, I'm sharing here. Yeah, uh, the screen. Uh, okay. Uh, uh, can you see my screen? My new screen? What I'm showing now? Okay. So this is ideally how signal strength is being displayed. But look at it. Look at the noise. Look at the signals, the transmission without without um, superposing it on the noise floor. You can see each signal is separated. Like you can see the amplitude and the signal strength in dB. Don't worry, you can see you are seeing negative in front of it. Don't worry about the negative. We talk about the negative because it's relative, right? Talk about the negative later. But you can see on the left side here, moving my mouse, you can see it's negative, and then you can see signals in different ways, in different spectrum, and but then there's no noise. Okay, let me superpose it with one that has a noise. Okay, haha. The same signal that you saw earlier. Let me put it in the 5 gig. That was what we were looking at earlier. So the same signal you see earlier. Okay, that is the same signal, but then you're seeing a lot of reds. So at the bottom here is the noise that is consistent at the bottom here. So the noise law is around, if you look at that measurement here, it says neg 85 or neg 8, like neg 85. Can you see it? Can you guys see what my mouse? Yeah. Awesome. So that is the noise floor. That is a noise floor. But the signal, the green part at the top, can you see? It's way above the noise floor. So if you look at this particular range here, channel 10 to 11, 11 is precisely, you see the noise is a lot. Oh, it has jumped here. Another noise here. Can you see? Can you see the noise, the right parts, jumping and moving around? You can see the noise at the bottom. Okay. So the noise, the red one that you're seeing, it shows the noise on the background, but the signal on top of it is clear enough. So you're moving away, if you're moving away from your transmitter, your signal strength will start getting weakened. Remember, I told you about this free path loss, free space path loss. So as the signal is spreading out, is getting weaker and weaker. So your signal strength, the amplitude will drop. And when it drops, it gets closer to the noise floor. When it gets closer to the noise floor, that is when you say, I can't hear you. Can you speak louder? Do you get a concept of noise floor now? Right? Thumbs up, thumbs down. Awesome. Great. Okay. So let's go to awesome. Perfect. Okay. So let's talk about the signal. Awesome. I like that. Good. So let's go to the concept of signal to noise ratio. So that is the signal quality. So the signal, that is the actual transmission to the noise floor, the difference, the delta between the two is called SNR. You're going to be hearing that a lot henceforth. SNR. SNR helps you to know if the signal is good enough or is poor. We usually signify good signal when the signal strength is about 25 dB higher than the noise floor. Then you can easily understand it better. But when it is just about 10 dB away from the floor, it's it becomes very difficult to understand. That is when you say, can you say that again? Oh, sorry, I didn't hear that. Come again. What did you say? The same concept of saying, come again, what did you say? Happens in transmission, happens in radio frequency. When the transmitting device is sending signal and the signal is not received properly, at the other hand, they say you send a signal back, they transmit. Or so there's no call. I have not gotten there, but I'll explain anyway. There's a call contention base. Okay, so when your transmitter is sending signal, we wait for an acknowledgement. If you don't get the acknowledgement within the time frame, you resend. Acknowledgement is what we use in transmission to know if it has been received. If the receiver does not send an acknowledgement, like I do that a lot. I tell you, do you understand? And then you guys give a thumbs up. That is acknowledgement. If I did not get a thumbs up, I repeat myself. Exactly. That's the same way the RF transmission actually happens to. So if the transmitter, maybe your phone or your mobile device or whatever the transmitter is, the transmitter can be your phone or your antenna, whatever, the base station, doesn't matter. What matters is that they can both, in RF, as I explained earlier, they are both transceivers. They are both the transmitter and the receiver, okay? Unlike acoustic in sound. So if the transmitter sends the signal and is not getting the acknowledgement within a short time frame that is specified, it is sent again. It's called retrials. So retrials happens when the signal is when the SNR is poor. So and that is what slows down transmission. So when you are very far away from the transmitter, then the amplitude, the signal strength of your transmission is very low and becomes very close to the noise floor. Let me show you something that will make it a lot easier for you to comprehend what I'm saying. Oh, thank you. Okay, I'll show you something. Uh, okay, good. Let me find one with a very weak signal strength, okay? And then you see how it is close to the noise floor. Let's try this guy. What's the name? Uh, anyway.
Imane, sir.
So, is that for me? Can you see my screen? Action tag. Okay, let's filter to this particular. Let's filter to. Oh, I lost it. Let's filter down to dollar Wi-Fi. Okay, okay, here you go. So can you see the signal here? It is this one here. It's gyrating around the next 76, next 75. So that is the signal here. Can you see? Can you see my mouse? You can see that it is very close to the noise floor. Look at the red parts. Look at that red part and that dome. You can see that it's very close to it. Now, a signal transmitted in that, it means that that transmitter is perhaps very far away from me, or the transmitter is transmitted at a very low amplitude. So this particular signal is going to be very, very difficult for the receiver to be able to differentiate it between the data that is being transmitted and then the noise floor. And it's going to be a very slow transmission. Do you understand what I'm saying now? Better? Okay. All right. So let's go into the next concepts, and then we can. Okay. So I've more or less explained what the receiver sensitivity is, right? So it's when we have a very strong signal, then you have a better signal strength. So if you're in the market, I just explained earlier, uh, you have to increase the volume. That's pretty much the way it is. So the receiver sensitivity is a function of the uh, the data rate that is coming out, how much of data that you can send. So receiver sensitivity is typically defined by the network speed. So people have seen that in iPhones, and Samsung devices, or whatever devices that you have. The vendors actually specify their receiver sensitivity thresholds at various data rates. So the higher data rates requires more power, and sometimes that is what burns the battery, right? Because the transmit at high data rates. And in order to conserve the battery power, you kind of reduce the um, the transmitting signal strength. And that is why sometimes when your battery is very weak, you don't get good coverage. You don't, the performance is reduced because you're trying to conserve the battery, going to the battery power save mode and stuff like that. That happens on devices. Anyway, so the different speeds usually um, use what called various modulation techniques. I'm going to be talking about modulation techniques and encoding methods next week. So with higher data rates, that means it's being susceptible to corruption because you're trying to send transmission with very higher modulation, and higher modulation is let's look at it from this perspective. Uh, say from this way: when somebody is talking to you in a native language, like let's say speaking Yoruba to you, the basic Yoruba, and that is the lower modulation technique. Your brain does not need to function in a very complex way to interpret what the person is saying. Okay, basic. However, if I decide to speak Ijebu to most of you here, right? I'm not sure that most of you understand Ijebu language. Okay, if you do, you probably have to put in a little bit effort to listen very well to understand the dialects, right? The same way, if an Ondo guy decides to speak the Ondo language, you need to put in extra effort to understand, to flow, because what is being spoken is no longer a basic language for you. Aha. Let's make it a little bit more complex. Let's say you now have like a North American, speaking North American English to you, and is speaking normally, smoothly, slowly. You have to pay attention. You're watching Netflix. You have to pay attention to understand what the person is saying. You have to pay attention. Unlike when you back and or like when you back the TV and what's this guy is talking Belu or whatever is talking on the TV on the Yuba movie, you can back and still be following the show, right? But then you want to be sure that you're following the movie very well when somebody is speaking North American English or British English to show that you're not missing anything, right? So you're putting a lot of effort. That is because the modulation technique we use is a little bit complex. You need to be able to decode the signal that is coming and pay my attention. So it's chewing up a lot of memory. It's chewing up a lot of CPU usage because your brain is working. So I'm talking down of your brain. It's chewing up a lot of your brain, your capacity, So you have to drop some other things to focus and understand what is going on. Oh, let's make it a little bit more interesting. Let's say perhaps the person talking is not speaking in French, right? That makes it even more difficult. If let's say you only understand basic French or basic Spanish, right? Habla English, you know, you're like, oh, no habla English, sir. I like, oh, I don't understand it. I don't understand English. I only speak Spanish. No, okay. Oh, like I don't understand Spanish. I only understand English. Anyway, what am I saying? The more difficult it is, the more difficult. The more it is easy to miss out the information. The missing out the information is tantamount to having the corrupted signal. Do you get what I'm saying? Right? So missing out the information is tantamount to what? Having a corrupted signal. So when a signal is being transmitted and you have corruption in between it, It means that you don't get the whole picture. You have to either send an acknowledgement or send an acknowledgement with an extra information that say, I missed content 3, 5, and 7. Can you transmit that signal back to me? That is the concept of wireless transmission. And that is what I want to talk about. I'll be talking about more next week. Okay, so talking about this whole idea, it's basically what surrounds the way RF transmission is done. What we call SSQ, that is the signal quality. It measures the pseudo noise codes. So the pseudo noise code correlation quality received by a radio. So let's simply put it. So signal quality measures factors that are affecting the coding techniques. So when you talk about that, several coding techniques like banker code or complementary code keying, like CCK, you probably must have heard that before in school or stuff like that. But bottom line, what I'm saying is that a low signal to noise ratio will indicate the SQ matrix, that is the signal quality matrix. Is it clean? Is it dirty? Is it going to cause a lot of retransmission? Is the you understand the whole idea of what I meant by the signal quality and then the transmission and how it all relates to wireless transmission. Any questions so far before I go to the next concept of antenna and voltage standing ratio? Any questions so far about what we just spoken about? Okay. No question is bad. Silence is worse. Are we good? Okay, we're good. All right. Okay, awesome. Let's quickly rush through this last concept and then we can go for a break. So, voltage standing wave ratio. What is voltage standing wave ratio? We see it a lot. VSWR. What does it mean? That's a very simple thing. It is a concept around antenna installations and stuff like that. Yeah, as I mentioned earlier, we talk about wireless, but wireless does not exist or cannot exist without wire. Okay, so what you're trying to do, you're trying to reduce the amount of wire you're using. That is when you bring in the concept of wireless. Wireless cannot exist without wire. Remind yourself about that. Wireless cannot exist without wire. So you need to understand the behavior and the characteristics of wires. Okay. So one concept about wire is the voltage standing wave ratio. So voltage standing wave ratio measures the impedance change in the alternating currents. Like I said earlier, I'll repeat myself again. Impedance is the electrical resistance. So if you hear the word impedance, it means the same thing as resistance. Like you're pushing back. And it is measured in ohms, right? Um, when the transmitter generates a signal, okay, it travels through the cable to the antenna, to the transmitter. It travels through the cable to the antenna, okay. Some of this energy is reflected back in the cable through the transmitter due to what we call the impedance, right? The impedance mismatch. It's called impedance mismatch. So you're transmitting through the cable, but it's being reflected back. Remember when we talk about the reflection and stuff like that? It happens also in cable. It's being reflected back because of impedance mismatch along the signal path. Okay? So this mismatch are typically due to probably changes between the transmitter, the cable, the antenna, whatever. Okay. And we talk about this reflection in what we call a voltage reflection coefficient, rho. You probably have seen that sign before, rho. Yeah. So it is the ratio between the voltage of the reflected wave signal that is coming back and the incident wave other points along the cable. So let's say these points in the cable, what is the VSWR? We talk about the reflection coefficient here when the signal is going back instead of going forward. But at that point, you need to know that spot. In an ideal system, which does not exist, okay? In an ideal system with no mismatch, all the energy, all the signal that is being sent is delivered to the antenna. And in such case, you see there is no reflected energy. You cannot achieve that. We try to achieve that, but you cannot achieve that. So the cable is matched, meaning the voltage reflection coefficient is zero. That's not possible. Okay. The return is called the return loss. Okay. And in an ideal situation, return loss means zero. That is, nothing is returning back. But there's always a return loss. There's always a reflection. Okay. In designing the PCB and putting in the antennas and the loss and the likes, we call it the trace. TRAC. So you look at the trace and insertion loss. So many things have to be in place that will cause the reflection in the path to the antenna. You have a lot of things, the inductors and so many other things in it, in the path of the cable, the trace itself, that results in what called insertion loss, right? Because you're inserting a lot of things in between the parts to get it before it gets to the end. One of the things that we impart is filters, right? Because when you send a particular signal to the antenna, you want to filter it such that only the band pass, only the particular frequency is allowed to get to the antenna. Let's say you're creating an access point and you want it to only transmit on 6 gigahertz. So you're going to put a filter that filters anything below 6 gigahertz and filters any transmission above 6 gigahertz. That filter is going to cause insertion loss, right? It's part of those that are going to cause the reflection back. There are so many things in the path, right, that will cause the reflection. So you don't just have a single cable connected to the transmitter and then to the other end of the antenna. There are so many things in the path, okay? So, bottom line, what I'm saying is that you need to understand the concept of VSWR, that is the voltage standing wave ratio. And the reason why is because you need to understand what we call the return loss. The return loss is the decrease in the signal power due to the impedance mismatch. Okay, and if you look at the table here, you see what I meant when I have ratio 1 to 1. That is 100% power is radiated. The loss power is zero. The return loss is infinite. Power loss is zero. You cannot achieve it. Don't deceive yourself. The closest you can achieve is 1.5 to 1. It's typically not achievable. So you start thinking about 2 to 1, 6 to 1. Those are the things that looks just like this. I'm just loading one for you. If you heard about it, oh, awesome. See, you guys are so smart. Uh, okay, let me show you how Wireshark looks like. Okay, you can see the way transmission looks like. We're going to talk about it a lot later. This is an example of how a signal and Wireshark looks like. And you look at the radio tab, you can see the data rate, the channel frequency, you can see is 2.4 gigahertz. Okay, 2412 is the full megahertz, and you can see it's under the 2 gigahertz spectrum. The noise, ah, that's the antenna noise, not the noise floor. So don't mix it together. And then we can have so many information from it. The fire rates. Yeah, can you see this is it's in a noisy environment, then the noise floor is so much. Let's find another one. That's there you go. This is a good one. See, the noise floor is around 95 dBm, and this is the QS non-function. We can talk about all this later. So, but this is typically a software that's used to analyze transmissions generally. Another one is acrylic and wind field lights. Okay, so acrylic and wind field lights. I'm going to put it on the lab for you to play with, so you can have a look at it and see how you can use it. You can install it even on your laptop. Okay, you can install it on your laptop and see how you can use it to get the same data that I'm showing to you. Okay, so back to this. So acrylic, as I mentioned, and then the Wi-Fi lights. They are free tools. Wireshark is also free. Echo is not free. Okay, so you can install these applications 1, 3, and 4 on your laptops or your devices and try it out and see how it looks like. Play with it. Just familiarize yourself with it and see how it goes. There are different ways to analyze signal. Signal strength is measured on our device can see the signal strength from the wireless access point or whatever. It's pretty much very easy to use. There are different ways. We use I'll call it. We use the Wireshark to do some testing uh, for analyzing the signals, packet capture analysis, technique 3. We use Wireshark to do that. You can use acrylic or wire lights to identify channel interference. I would like you to do that. I'm going to put it in a lab, and you can play with it on on your laptop or even your phone or stuff like that to see how interference are being dealt with. Okay, and you can also use as Echo Heat Mapper and some other free applications that you can actually use to create heat maps and stuff like that on your devices. Okay, multi-app output MIMO technology, about the antenna types and applications from Omni to directional antennas. So that will cover the basics, the fundamentals for this week. The RF basics that I want to talk about. Then the next week we'll start with something a little bit deeper. Okay, so let's see. We're good, right? We can proceed, right? Everybody's ready? Awesome. All right, let's go. So when we talk about the line of sight, we usually focus on what we call the visual line of sight. So remember the way I've been explaining to you all this while, radio frequency and light, they have so many characteristics in common. Okay, so for you to kind of comprehend what I'm saying in terms of radio frequency, I'll be using a lot of visible light scenarios to kind of explain what I'm trying to um, depict to you. Okay, so visual line of sight, LOS, as we usually call it, it refers to an unobstructed straight line through which light can travel. Okay, from one point to the other. Okay, uh, while this line may appear clear to the naked eye for us to see, in atmospheric conditions like refraction, diffraction, or even reflection can slightly alter it. You know, it may look like it is straight, but it can bend, it can be refracted, it can be reflected in atmospheric conditions. For instance, okay, if you've looked at a like the Third Bridge in Lagos, right? you may probably have noticed that distant objects appears to be shimmer, or you can see some wave due to it. I don't know if you've seen something like that before, where it looks like the bonnet of the car is radiating some kind of. You've seen it before. Awesome. Yeah, it's supposed to be straight line, but it will kind of affect the signal. This is an example of how visual line of sight can be affected by atmospheric conditions. So I want you to keep that picture in mind. Okay, that is an example that you have seen. Okay, I'm going to be talking about what we called RF line of sight. Now you use that visual line of sight concept, okay? Use that visual line concept to understand uh, uh, RF line of sight, okay? Remember again, you see, you probably see it, you see it often on a long roads, right? And asphalt roads where you see the object, it will appear a little bit like a wave, like it's coming out from the bonnet or from the top of the car, depending on you will see something a little bit. The light's supposed to go straight, but that atmospheric condition is changing the direction of the light, is altering it a little bit. So in RF communication, visual line of sight does not really guarantee signal integrity, because wireless communication relies on what we call the RF, the radio frequency line of sight. And this includes an area surrounding the straight line. So it is not a straight line, it is it includes that straight line and then the area surrounding that straight line between the two transmitters. So anything that obstructs RF line of sight, right? This is what I mean. This area. See? Can you see it now? Right? And then awesome. And then this area. Okay. So you have two transmitter. Ideally, this middle line is what the line of sight. But in RF, okay, in radio frequency, the line of sight includes all this area here up to, let me get to the other side. It's like a it's elongated, it's like oblong. It's not really right. I don't put it. So that's the way RF line of sight is. It's not a straight line. Okay. And then for point-to-point RF link, maintaining the RF line of sight is very critical. We need to make sure that we achieve that point to point. Even a little obstruction in the RF can actually affect the transmission. So this includes a zone around the visual line of sight, and it is known as Fresnel. Can you see the spelling? That's the pronunciation. Fresnel. So Fresnel zone is an elongated football shape. You know this American football? It's an elongated football shape, like egg kind of a thing, but pools, right? Around the surrounding signal line. So, like I said earlier, keeping that zone clear of obstruction is essential to avoid signal degradation. If you don't have it clean, then there's going to be a problem. Okay, let me explain Fresnel zone a little bit. So, Fresnel zone is not just a single line, but rather it is an elliptical area around the visual line of sight. So, with the Fresnel zone being the closest to the line of sight, that is what I was explaining earlier, uh, that you have the visual line of sight for. I explained in when you're looking at normal lights and you're traveling on the road. No, the most critical for signal is the Fresnel zone. Now, obstructions within the Fresnel zone can actually cause issues like reflections, scattering, diffraction, and all of which I've explained earlier when we started today can reduce the RF energy reaching the receiving antenna, and that may actually cause signal loss or poor quality. If it is totally cut through, it will cause a signal loss. So let me give an example. Let's think of a point-to-point link. Okay, in Ibadan. Okay, I don't know how tall buildings are now, but I remember Cocoa House. Maybe it's not the tallest building in Ibadan anymore, but then it used to be the tallest building. So let's say you have an antenna transmitting in one side. Okay, yeah, okay, and then there is a tree in between. Okay, this is Cocoa House. Okay, you're transmitting and it's transmitting to the other end of another building. Okay, but there's a tree here. If you see, the final zone goes all the way here, and that tree is eating into it. Can you see from the bottom? The tree is eating into it. So that is what I'm trying to show you. Okay, so if the tree obstructs more than 40% of the first final zone, then it could actually significantly degrades the RF link performance. Ideally, ideally, no obstruction should exist in the first final zone, irrespective of whatever you're trying to design. So always make sure that you know that calculations, you know how to represent your final zone, right? Especially in environments where you know that trees naturally grow and stuff like that. So those are the things that can impede your transmission. So now start thinking about it when you don't have network on your phone and you're complaining. You should know that something is obstructing the transmission from the antenna. Maybe your neighbor just built a house that is very tall and is blocking the signal. And they're like, oh, that makes sense. That is why, oh, I see. Oh, is that tree that is growing that is causing? So you can start relating it, okay? So things like that, people don't see them. But you, as an RF engineer, you should start seeing things from that perspective. So how do you calculate friendly zone? Friendly zone, you can, this is a typical calculation that we use. You don't need to cram it. Please don't cram it. I don't think you should. Just know it. If you need to remember it, Google it. Okay? I don't believe in cramming. Okay? Cramming doesn't show that you're smart. Use the tools that you have. Using the tools that you have is how you show that you're smart. Okay? So Google it. Google is a tool. Try to just check the website, check the internet for this calculation. Okay? So what am I saying? So you have your distance. Can you see? Do you want a D2? Yeah, a D2. That is what you need to do the calculation of your Fresnel zone radius. So it's a little bit more, but I just summarize it here as the 72.05 times the distance in apart in miles over 4 times the frequency of the signal that you're trying to transmit. And that's how you calculate your Fresnel zone in feet. Any questions so far? Oh, good. Okay. Let. Okay. Sure. Go for it. What's the question?
Yes, sir. What of the case where in potential the location you want to transmit to is between, yeah, is in the valley? That means you have two height, then you have a valley in between. Uh, Some
Ah,
areas in Ogumosho, I know years back they had that challenge.
so when you're doing that, it's the function of, okay, what I've brought is a concept called Earth bulge. Okay, Earth, type it for you, Earth bulge. Okay, so let me explain that. I like it when I explain things in the fly. Okay, so Earth bulge. Okay, it's another concept that we consider when we are doing RF uh, design. So you need to understand the landscape. Is there a mountain or a valley in between the transmitter and the receiver? So for the point-to-point link, so you don't just put antennas on the mast. It is calculated. You need to first of all um, understand the terrain and ensure that there is nothing in between the transmitter and the receiver. So we do like what surveyors do, that you look at the lens to see. So you go and compare the heights at which you do the calculation, at which the earth budge or does not interfere, does not come into the final zones. Either it is a mountain or a valley, to make sure that there is a line of sight between the two, that is point to point link, nothing is blocking it. A way to achieve it, if there's a mountain, is to raise your mast a little bit higher and make sure that you have a point to point. But if it's the valley, it's usually a very easy um, uh, design, because in the valley, in between, it's even lower. So it should not tune into the friendly zone. It just make sure that your antennas are both aligned and can have a point to point connection. Did I answer your question? Awesome. Okay. All right. Yeah, sorry, it's the watered down version. I don't want to go into so many technicalities. I don't want to push you guys away with too many information. So, in case I don't mention anything that you think is important to you, please call my attention to it and I'll explain. It doesn't have to be in the material I'm sharing. You just tell me. I'll do my best in explaining to you. Okay. All right. So let's talk about the concept of beam width. Beam width. It's a concept that I really want you to pay attention to. It's let's start with the concept of light, the touchlight. It's easier that way. So, beam width is the width of an antenna signal beam. Um, it defines how narrow or broad the signal focuses. Now, the key word here is the focus. So, if you have a touchlight, you can turn. I don't know if this is the kind of touchlight, with a shiny, silvery kind of touchlight that we used to use those days. You can turn it uh, in to focus. Oh, good, great. It will focus the beam width, and you can turn it such a way that it can spread the light. You get that analogy? That narrowing and broadening concept of the light is beam width. When you are driving cars, they will say that the beam lights. I don't know if you have heard that concept. When you're talking to folks, they talk about beam lights or something like that. So it's about the beam of the lights, how it's spreading and how it's focusing, and that is what the beam is all about. So beam width Excuse me. Beam width is specified in two directions. If you see what I'm saying, like that. So it is horizontal and vertical, and each measured in degrees from the signal strongest points outwards. So the point at which is coming, see my hand as if it's a torchlight. So the signal strongest point is that bulb that is coming out, right? And there's like a funnel-like thing that is placed on the bulb. If you remember your torchlight, so that center is where is the strongest point, and it's going outwards. While the signal drops by half, okay, the the half is the 3 dB, but I said drop. I didn't say gain. So if I say drop, it means I'm subtracting. That is minus 3 dB. You get understand? Remember when we did the RF calculations, I told you when you when you subtract, that is a reducing, right? When you add, you're increasing. So when the signal drops, that is it drops by half. When doing calculation, 3 dB means what? Times two or plus or minus two. Remember the calculation, right? So the half concept means that when I subtract 3 dB, that means that I have halved the signal. Hello, am I with you? Okay, great. I just want to be sure that you are getting that concept because it's very important. These are very important things that I want you to follow me. So when I halve the signal, awesome, awesome, perfect. When I halve the signal, I am saying that I am reducing it by 3 dB. So these negative 3 dB points, they're also called the half power points. So it's called what? The half power point. And it marks the boundary of the main lobe or the primary signal area. Okay? Look at it here. Look at this. Yeah. Uh, 3 dB. Can you see? 3 dB. 3 dB. So this is half. Huh? Do you understand? That's the line of the 3 dB. But when you're dividing it by 10, that is 10. Do you understand? So here, all the way down is half of the beam width. Does it make sense? Okay. So yeah. I think you guys get it. Yeah, you guys get it. So this is very important because this is all idea behind the charts. I'm very sure some of you that have done electrical, you probably must have done these polar charts. I'm explaining from different perspectives. I know you probably must have done it from a theoretical perspective and this from uh, complex calculations. I'm not interested in that. I just want you to get it and use it usefully because the theoretical way of doing it may get a little bit confused. So I want to focus on what you need. So when you look at the polar charts, go ahead, Israel. Tell me, what is it?
Oh my God, so
Okay, all right. I'll continue. Looks like Israel is really okay. All right. So when selecting an antenna, so one of the things that as an RF engineer we refer to is what called the manufacturer's spec sheet. So now the spec sheet actually usually includes the horizontal and vertical beamwidth value of the antenna. So we use that polar charts to understand and interpret the beam width of the antenna, to know the performance of the antenna. How is the antenna going to propagate the signal based on a particular frequency? Is it going to spread it very wide? Is it going to spread it very narrow? And stuff like that. Those are the things that I'm going to be talking about today. And then some will spread it around, some will spread it in a focus angle, some will spread it a little bit wide. So each antenna has different beam width characteristics. Most charts feature solid circles markings, right? That shows the signal drop level like neg 10, neg 20, neg 30, and then we have like dotted circle for immediate values like neg 5 dB, neg 15 dB, all sorts. You understand the concept of what I'm saying, right? So the most important thing is to locate the peak signal. The peak signal, okay? So the peak signal, you can find it at the central point of the maximum signal, the maximum strength of the chart. This is the strongest point from which the signal gradually weakens outwards. So the first thing is to do to find the peak signal. The next thing you should do is to find the 3 dB, the half, which I showed earlier, right? The half. Now you move along the signal pattern in both directions, both horizontal and vertical, until you reach the point where the signal decreases again by 3 dB. Okay? That's how you keep on following it. Keep following it like that. That's how we measure and look at it. Another concept that I want you to look at is this guys here. It's like how do I put it? Like uh, pineapple leaves, right? At the bottom of the pineapple. The pineapple is the one that stays up, and then the whatever comes out at the side. They're called the side lobes. The main lobe contains the strongest signal, but the antenna itself produces what are called sides or rear lobes. Now, these lobes represent lower signal area outside of the main beamwidth. So, by it produce additional like kind of ambient weaker coverage around it, just around it. Okay, okay. In some cases, the lobe can actually be functional and even beneficial in extending signal coverage in some directions. So usually purposefully use antennas that have some particular kind of side lobes so that we can achieve some coverage, right? So we have different types of antennas, and I want you to have a look at them. We have antennas that's omni. Okay, omni means it goes in 360 directions. For the horizontal, the omni antennas transmit like donuts. You know, donuts that has holes inside. Let's see if I can do this one here. Yeah, that is the way omni is. So inside is where the antenna is. Okay, and then they start broadcasting outside like that, like a donut. So if you put it properly horizontally, it should look like that. That's the way the transmission is done. Okay, that's an example of how omnidirectional antennas actually look like in transmission. I can show you like this. Can you see? It's going to look like this. So this is how the transmission of Omni looks like. Do you understand what I'm saying now? So the antenna is in between, it's in the middle. The antenna is in the middle, right? And then the XY axis is on top, and then it radiates in 360. But it does not go up because the vertical beam width is between 70 to 90. But the horizontal beam width is 360. That's what I'm saying. So look at it there. The horizontal beam width is 360, but it doesn't go up that much because the vertical beam width is what between 7 and 80. Do you understand what I'm saying? Okay. So we have others. We have like patch antennas or panel antennas that they're kind of focused in one direction, like 30 to 180, and then they just go straight. They go like within 6 and 90, but they don't do much. So this is an example of a patch antenna. Okay, it goes straight, and the angle maximum is like 90. Okay, so beam width is just straight. It doesn't go to the back, unlike Omni. Omni does 360, but patch or panel, they just do whatever they're facing. It's usually used for wall to wall, building to building. Okay, point to point, you use that, and you don't want the vertical point to point really that is short, because if you make it point to point and it's long, then the Frene zone may be impacted, and that is why we use Yagi often. We use Yagi often for point to point that is not that far. This is Yagi. Yagi is usually good for point to point that is not so far. But if the very far point to point, we usually use what we call sectors. These are sectors antennas. They go very well horizontal, not too far, not too wide, and they don't go too high vertically because they're just 7 to 17. They don't even get up to 20 degrees. So why are you using it? So that you don't have obstruction entering the friendly zone. You understand? So that's why you use this kind of antennas. You probably see parabolic antennas a lot as well. We use that for long distance communication, like miles apart, kilometers apart. We use parabolic. You probably see that on Nitel. I don't know if Nitel says it. Nitel dishes or FRCN. They use that a lot. It looks like a drum covered with a sector antennas that is used to. Let me see if I can find you sector antenna. Example of sector antennas. So you see they have a very narrow vertical beamwidth and horizontal beamwidth. You use it to kind of focus like cylindrical kind of a thing. Can you see it's very focused, the pattern, can you see? And then the side loop doesn't even go that far. It's just very focused. Okay, so let's go back to this and then okay. So now that you've spoken about antennas, let's talk about antenna polarization. Polarization means, is it vertical? Is it horizontal? Is the orientation of the electromagnetic waves that you're actually concerned about that is being radiated from the antenna. So it's very important. Now that you've understood the concept of the Frene zone, you don't want to turn your antenna in a wrong orientation. If you put in the wrong orientation, it's supposed to be horizontal at, let's say, 90 degrees and you turn it the other way. So you know that there's likelihood that there will going to be obstruction and the 90 is going to go down instead of going sideways. You don't want it to go down, you want it to go sideways. So orientation is very key in RF transmission. Polarization is a concept that we are concerned mostly about in outdoors. We are not concerned about it in indoors per se. But in outdoor point to point or point to multi point scenarios where we have like a slight misalignment can actually cause a very significant drop in the receive signal level. So if you observe like receive signal level, we call it RSL, that is 10, 15 to 20 dB lower than expected, then you should think in your mind that there is likelihood that I have orientated the antenna in the wrong way. Because if you have the antenna crisscross, then they will not see each other correctly. So you have reduced what is matching. So vertical is probably like 17, and then the horizontal is 90. So both of them will only see each other at 17. Then there's a problem. But if you arrange it properly, you match it properly, then you probably may see each other at 90 or stuff like that. That's the concept. Hope you understand what I'm saying. But in indoors, polarization really have less impact because ah, most often signals are actually bounced off surface anyways. So polarization doesn't really matter because there's reflection. Okay. And most antennas used for indoors are actually omnidirectional antennas. So it doesn't really matter. Omni, it's they do not ship one. So and they are vertically polarized, and when they're mounted on the wall or the ceiling or whatever, doesn't matter, or your laptop antennas and stuff like that. They're usually mounted vertically with the screen of your laptop. So doesn't matter. It will still get whatever you want. Okay, let's talk a little bit about the antenna diversity. What do you mean by antenna diversity? Your indoor wireless networks, they often experience multi-path interference. And multi-path interference as a result of reflection from furnitures, from walls, from anything, any objects that you have in the house, your curtain, your whatever. As long as the wavelength is longer, uh, is long enough to not penetrate through that particular material, okay, then it will definitely get reflected, okay. And when it reflects, it can cause a lot of plus or minus. But to mitigate the effect of multipath, so we use what we call antenna diversity. Sometimes it is called spatial diversity. I know some of you must have heard about that. Spatial diversity. And so it's just another name for antenna diversity. We use antenna diversity in with multiple antennas and receivers on devices to enable it to select the antenna that is receiving the strongest signal at the given point. So you have the antennas, like 3 or 4 antennas, antenna diversity. What it does is that when the signal comes, whichever have the strongest signal is going to be used to receive the signal. So if the other one does not receive it very well, uh, based on the orientation or based on the reflection, MIMO or whatever, it discards that. It takes the one that has the strongest signal, and that is what we use. That is what enables and improves transmission indoors most of the time, because in indoors we have access point and stuff like that that have multiple antennas. Let me give you an example. You don't see this often, okay? This is just a prototype. This is just a prototype. This you don't see this often. So this is something that you probably see. So when you have different antennas, and then you don't see this often. This is a prototype, and yeah. Uh, so when the signal reaches different antennas, the one that has the stronger signal is being used to receive the signal, and the other ones are discarded. By the way, those are dipoles antennas. Okay, so there are different types of diversity. The diversity can be switched diversity, that is the received diversity. Before we have 802.11, IEEE 802.11 radios are often used to switch the diversity. So in that scenario, the access points will monitor multiple antennas and then pick one with the stronger signal. That is a frame by frame basis. The second one is transmit diversity. In transmit diversity, when transmitting, only one antenna is active. The access points will transmit with the same antenna that previously received the signal. So that way, it knows that if this antenna is receiving the signal strongest the most than the rest, then it doesn't make sense to use the other antennas to transmit. You use that one that receives the strongest signal most recent, and that is what we call transmit diversity. There are a lot of ways to get that done. There are guidelines for diversity setups and stuff like that. So yeah, we'll talk about most of that later. Okay. So far so good. Any question? All right, let's talk about the azimuth and elevation charts. We started looking at it earlier. So in RF engineering generally, we use azimuth and elevation. So we use them essentially as tools to visualize the antenna radiation pattern and then understanding its coverage capability in both horizontal and vertical plane. Now, uh, we can't see radio frequency, so that's a problem. So we need to be able to uh, uh, visualize the 3D pattern. It's a 3D. It's not just a Cartesian plane. It's a 3D pattern. So we need to be able to visualize how the transmission is done. Okay, and is this azimuth chart is one thing that we use, and the elevation chart to understand the angles very well. The azimuth chart or the horizontal pattern kind of shows the antenna coverage area. Yeah, it shows the antenna coverage area from the top down. So you are looking at it from top down. Okay, so it displays how the signal radiates 360. Do you get it? Around the antenna, around the antenna on a flat horizontal plane. So horizontal plane. It we use it um, to for positioning omnidirectional antennas in most times. Okay, because omnidirectional antennas they're 360, and it's very useful to look at it from that perspective. So three azimuth as a horizontal pattern of the transmission. Okay, top down. You're looking at it from top down. Always remember that. Okay, the coverage area from the top down. In elevation, elevation is a little bit different because elevation provides a side view of the antenna radiation. So it illustrates the vertical. So like you cut it in the middle, boom, and you're looking at it from the side view. I want you to go back to your engineering drawing. We used to do the elevation view, right? And then the side view of the azimuth of your technical drawing. So see it as the same thing as what you're doing here. So you're having a look of the azimuth, the horizontal, and then the vertical, the elevation. The horizontal view and the elevation, the vertical, is the same. You're just using different uh, word to describe it, but exactly the same thing. Elevation view in your engineering drawing, and then the horizontal view in your engineering drawing. Horizontal view is called azimuth, and elevation maintains the elevation. Both charts are very crucial for antenna alignments, especially when you're dealing with a point-to-point or point-to-multipoint setups, because you need to be able to aim the antennas with precision, and that is what you use to avoid, signal loss, reduce the interference. You need to ensure optimal signal focus, because that focus is very important. That focus is very important. If you don't focus point to points together the way it's supposed to be, then it's misaligned, and then you don't get the communication. You need to get the communication. Imagine that you have a wire that is connecting two points together, right? They have to be focused, or put such a way that they are aligned, and that is the reason why we do all these azimuth and elevation charts to ensure alignment within antennas. Do you get my point? Okay, so for instance, let's talk about omnidirectional antennas. Like if you have awesome in omnidirectional antennas, for instance, the azimuth, um, which will show the circular pattern radiating evenly in all directions. So it covers the 360. So that is what to use. In elevation, the elevation is the cut through, right? Remember that I showed you the donut shape thing. So it's a narrow vertical. So it is going with narrow vertical spread, and it indicates the signal strength that is being strongest is horizontal. Always remember that. So if you're talking about the patch panel, in the patch panel I showed you earlier, so it's a directional antenna. It's not omnidirectional. Patch panel is a directional antenna. So the azimuth chart will show a very narrow focus pattern, because it's not like 360 like Omni. No, it's just one direction. Remember, it's between the maximum you can get in patch panel or is 180 degrees, right? So for a patch panel, let's say a 60 degrees azimuth beam width, the concentration signal is always in one direction, going one direction. But the elevation chart is going to be a little bit different. Elevation chart is going to be narrow too, because it's going to be a very narrow vertical. It's not spreading like the other, like Omni. It's very narrow with limited upward and downward spread. It's like you have focused it. So you focus it from going horizontal too much, and you're focusing it even on the vertical as well. So when you cut it through, it's very tight. It's not spreading too much. So that's the difference, and that's how you know that, oh, this is a directional antenna. In a parabolic is even much more focused, because um, uh, it's kind of it's between 40 to 25 degrees, right? So it's extremely focused, very narrow azimuth, and then because it's narrow, there's the focus is very good. It's good for long distance. The firing zone is not wide. Obstructions will not get into it. okay, easily because it's very narrow. You can easily point it like a laser. Okay, the point is directional. It's highly directional actually, not just direction. It's highly directional because we use it for long distance, kilometers, miles. You know, and in the elevation chart, we often show a very thin lobe, very thin. I meaning that if you make a small adjustment in the antenna angle, ha, and you not align it properly, you're going to lose the signal. So it is a very, very uh, it takes a lot of you have to be meticulous with it. It takes a lot of concentration when you're aligning it. You need to follow the calculations and make sure that you don't, misplace the antenna. It is very focused. That is the way parabolic antennas are. So far, so good. You're good. Okay, you're almost done. Almost done. You're almost there. Okay, let's quickly talk about connectors and I'll talk about grounding, and then we're done for the day. Connectors, we have different types of connectors to connect your antennas. Remember, I told you there's no wireless without what? Wire. And how do you connect wires to wireless? You need to be able to connect your antenna to your wire. It is at the point of antenna that everything goes wireless, right? So from the antenna, how what are the connectors we use to connect antennas? We have a lot of connections. But the commonest one is the SMA. Okay, the SMA submini macho version A. It's used a lot. You have different types of SMAs. You have the RP SMA, that is the reverse polarity. Okay, so that one is male, the other one is female. You do that a lot. We have another one called the N connector. It's used mostly in outdoors. It is waterproof N connectors, and it handles higher power as well. We also have the BNC. You possibly must have heard about the BNC connectors. Uh, it's usually used with a coaxial cable. Coaxial means copper axis cable, coaxial cables. You use BNC connectors with it, and then it can take a lot of power because of the kind of cable that it takes. The coaxial sometimes they are like 75 dB, so 75 ohms. Capable cables. So these are the kind of connectors that we use. We also talk about connector concentration. Connector concentration has to do with like uh, the poor quality of the smash connectors that usually cause signal loss. If you don't have the right connectors connected, if you connect your antennas to your cable, then remember what I talked about the insertion loss when we talk about the voltage standing wave ratio. So if the cables and the connectors they're using to connect your antennas are kind of mismatched or they are not the right connectors, then when the signal gets to that particular point, it returns back, it's being reflected back in the cable. And when it reflects back, it is also called insertion loss, the return loss. Okay, so you need to make sure that you use the right cable, the connectors. Weather proving, especially in outdoor connections, you need to use the correct connect weather proving. If not, then corrosion can happen. You don't want corrosion to happen to your connectors. When corrosion happens, it also increases the impedance. Then it starts changing the characteristics of the connector, and the signal loss, the return loss increases. So you need to be able to protect the cable. You need to be able to protect the connectors very well. Those are the considerations that need to come into place in places like southwest or southeast in Nigeria, where it rains a lot. It's wet. It's humid. It's closer to the Atlantic Ocean. It's humid. So if you don't choose the correct connectors, then it starts corroding. Okay. What are the installation best practices? Ensure connectors are properly tightened, sealed, you cover it very well, and stuff like that. One more thing I need to talk about before we wrap up for the day is called grounding. You probably are very familiar with it. Most of you that are in electrical electronics, or you have experience with grounding. Grounding is essential for safety because most of the time we don't see radio frequency, and because of that, we ignore so many things about it. But the truth of the matter is that if you don't have the proper grounding done, okay, to ensure any electrical discharge, such as lightning strike or power surge, then the whole equipment itself can actually spark and catch fire, and you don't want that to happen. Okay, so grounding is a concept that is very important. You need to know. You probably are surprised that you keep to learn about RF, and I'm talking about cabling. Yeah, grounding is a very good technique that you need to understand. And there are a couple of grounding techniques that I want you to understand to always remember. Antenna grounding, especially if you're dealing with outdoors, it's very important to ground your outdoor properly. You need to know how to hat your cables. Provide a low resistance part to the hat. Another thing is surge protectors. You will often ignore surge protection, especially in Nigeria. But it's very important to install a surge protector for safety, especially for your antennas. If you don't protect it, then an antenna kind of gets spoiled. That is downtime. Okay, you don't want that. You want to prevent surge so that you can safeguard the entire network. Okay. Another thing that is important that you can always consider is also grounding rods. So we use grounding rods, uh, we place them in the soil to create a reliable grounding system. Okay, so it's easier. It's better to use a rod because most of the concrete on the floor, most of the floor is concrete. We love to concrete our floor, and if we concrete the floor, then it's essential to use the grounded rod to be able to penetrate and get into the soil. Because if you don't have a direct access to the soil, then your lightning arrestors will not work because the floor is already concrete. You cannot dig into it, right? You cannot go into the soil. So that's why you need the grounding rod that you can use to pierce through the concrete floor and then redirect the sludge down into the soil. Yeah, those are the basic things that I think you should know for foundation for the basic things, and then we are done for today. You put